Disinfection. Of course, pathogens can either be removed by treatment process, like sedimentation, activated sludge process, or by filtration, or can be inactivated by disinfection agents. Okay? So they can either be removed by regular process or by disinfection, by inactivation, by disinfection process. And the very important definition of disinfection in drinking water practice refers to two activities. Primary disinfection, this is very important. What the meaning of this is inactivation of microbial life in water. Inactivation, which means that not make them active to regrow and to produce babies, to increase in numbers. The second objective of disinfection is doing a secondary disinfection. After you kill all the pathogens, you want to make sure that there is a disinfectant residual. So maintaining a disinfectant residual in the treated water distribution system is also called residual maintenance. In case if there is any leakage in the pipeline and there is an introduction of microbials or microorganisms, now this residual will make sure to kill that extra. Or if there is any regrowth, sometimes you will add a disinfectant and this bacteria or microorganisms are partially injured or they have spores around them. It is good to keep this residual to make sure that any regrowth is taken care of, and any bacteria or any microorganism that has spores around them and then they open their spores to look for food, the disinfectant residual will kill them. So there is current methods for disinfection. For example, disinfectants can be classified as an oxidizing agent, oxidize all the pathogens. For example, chlorine and ozone is an oxidizing agent. Cations of heavy metals, silver or copper, and physical agents, heat and UV radiation. So these are the classification of disinfection, either an oxidizing agent or cations of heavy metals or physical agents. The most commonly used disinfectant is free chlorine. Of course, you could hear chlorination all the time, and this is the most famous used disinfectant. And of course, the other common ones is combined chlorine, ozone, chlorine dioxide, and UV, ultraviolet light. And also combined chlorine is often limited to secondary disinfectant. Remember now, we should know what is primary disinfection and secondary disinfection. This is chlorine residual or disinfectant residual, and this is inactivation, initial inactivation of microorganisms. And we add disinfection in a reactor that's called contactors. We want to contact the microorganisms with the disinfectant agent. So, free chlorine, combined chlorine, and chlorine dioxide are most often used in contactors close to ideal blood flow reactor. Remember the blood flow reactor we mentioned previously? Such as baffled serpentine contactor chambers. And both of these type of contactors can be designed so that they are highly efficient, closely approaching ideal blood flow. Remember the blood flow? The blood of water is moving from one place to the other. UV light, I really like this UV light, ultraviolet. is often applied in preparatory reactors where short circuiting is a concern because contact time are so short. Okay? Let's look at kinetics. Since we are engineers, we have to also include the models, how to model disinfection kinetics. Of course, the mechanisms for pathogens and activations, we call it pathogens and activations, during disinfections are complex and still not well understood. Therefore, we have to do a kinetic modeling that we developed and are based on, of course, experimental in the lab. The famous straightforward model to describe the disinfection process is called Check's law. So, dN over dt equal minus k times n. dN over dt is the rate of change in the number of organisms with time. This is number of organisms, and this is with time. Of course, n is the concentration of the organisms. Same thing that here. This is change of numbers of organisms, and this is the concentration of the organisms per volume. And k, this is Check's law rate constant. And that's why it's minus, because the microorganisms are decreasing. And it's also assumed that this disinfection reaction is following a pseudo first order reaction. Of course, with respect to the concentration of the pathogens being killed or the pathogen being inactivated. If we integrate that, you will get the following equation, that ln concentration of the organisms, or the number of the organisms at any time t, we could call it time t, over the initial organisms numbers, equal this constant k time, the time that you need to check after how many hours the number of organisms will reduce to half, for example. N naught is the initial concentration of organisms per volume, and N is the concentration of the organisms at any time t. And how could you plot it? You could plot the log organisms concentration N over N naught, log or ln, versus time. Of course, if you want to do a better estimate of the K. So, due to the inaccurate measurements, the best fit often may not pass through the 0, 0. Okay?